Hi everyone, welcome to the mock interview series, and today we'll be going with a mock interview for the network security engineer position where you are working with different security devices like firewalls, IDS, IPS, and like email security, web security, these kind of different security devices you work with. Okay, so here today in this video, I'll be the interviewer and I have Praveen with me who will be the candidate here. So welcome Praveen, please tell us about yourself.
Hi sir, good afternoon. This is Praveen Yadav. Basically, I am from Haryana. I have a bachelor's degree which I completed in 2022. I also hold certifications in CCNA and CCNP which give me basic fundamental understanding of network and its concepts. Additionally, I have completed my CCIE security training from Networkers Home, which give me in-depth knowledge of network and security. During my training time, I learned about various technologies like VLAN technologies, layer 2 technologies, which are VLAN, STP, Ether channel, layer 3 like dynamic routing protocols, OSPF, AIGRP, and RAPE. Some additional protocols which I studied during my training time is IP, TCP, IP, UDP, DNS, DHCP, some security protocols like IPsec and SSL. Additionally, I have a solid understanding of VPN concepts as well as different vendor next generation firewalls. During my training time, I worked on EXXI server where I deployed virtual firewalls as well as email security and web security appliances. So this is how I completed my technical training, and after completing this technical training, right now I'm looking for an entry level job in a company where I can use my skill set for my companies and my team grow. This is all about myself.
Okay. So now the first question for you is, what is OSI model?
So, sir, OSI model, OSI stands for Open System Interconnection. It's a reference model used to understand how two devices are communicating with each other. So, basically, in OSI model, we have total 7 layers. So, we can start from layer 7, that is our application layer. The main purpose of our application layer is to give the user interface, to give the interface between the user and the machine, so can our user and machine both can communicate with each other. So some basic protocols of application layer, we have HTTP, HTTPS, DNS. So after this we have presentation layer. At our presentation layer, the main purpose of our presentation layer is to encode the data. If the data is in the human readable form, it will convert it to the machine readable form. And if the data is in the machine readable form, it will convert it to the human readable form. It will also do encryption and decryption for the data. So basically our SSL handshake take place in our presentation layer itself. After this, we have session layer. So at our application layer, the request is the user is generating the request. At our session layer, for that request, or at our session layer, our session layer is going to maintain, going to establish, and going to terminate the session for that particular request which is generated by the user at our application layer. After this session establishment, it will forward the request to our next layer, that is our transport layer. So transport layer, this is the layer 4 of our OSI model. In our transport layer, we have basically two protocols which are mostly used, TCP and UDP. TCP stands for Transmission Control Protocol and UDP stands for User Datagram Protocol. As a part of encapsulation, it will encapsulate the data into the TCP header, that is of 20 bytes. After doing this, it will forward the data to the next layer, that is our network layer. So basically at our network layer, we have two types of protocol. One is routing protocol and another one is routing protocol. So what is routed protocol? Under routed protocols, we have basically two versions, IPv4 and IPv6. And under routing protocols, we have dynamic routing protocols like OSPF, AIGRP, BGP. So routed protocols and routing protocols. So the data, when it reaches to the network layer, it will encapsulate the data into the IP header, that is again of 20 bytes. And after doing this, it will forward the data to our next layer, that is our data link layer. At our data link layer, basically as a part of encapsulation, it will add the Ethernet header and it will add up 4 bytes of FCS, that is our frame text sequence. So Ethernet header, in our Ethernet header, we have information for the source MAC and destination MAC, that is of 14 bytes, and our FCS is of 4 bytes. Total 18 bytes of encapsulation process we have at our data link layer. And here our data is known as frame. So basically at our data link layer, we have frame. Frame is the PDU of our data link layer. And what is the frame? Frame is the hexadecimal format of the data. So after this data link layer, the frame is got sent to the next layer, that is our physical layer. At our physical layer is responsible to convert the hexadecimal data into binary bits. It will convert the data into bits and it will share the bits with the connected device through the medium. So this is how our OSI model works, and these all are the 7 layers of OSI model.
Okay. So now the next question is how the OSI model is different from the TCP/IP model.
So basically, OSI model and TCP/IP model. TCP/IP model is the oldest model, and OSI model is developed later after TCP model. So basically, TCP is the model which is working over the internet. Everything works on our TCP/IP model. But with the TCP/IP model, we can't understand the flow of the data that much clear, in which we can do in our OSI model. So OSI model is used to understand how the data flow happens between two devices, and entire internet and our entire machine is working on TCP/IP model. So this is the main difference between OSI and TCP/IP model.
Okay. Now the next question is, tell me about some of the L2 security measures.
So L2 security, sir, at layer 2 we have basically port security. At layer 2 we have switches as a device which works on layer 2. So layer 2, to prevent our switches, we have a port security concept. What is a port security? In the port security, what basically we can do is that if, like, let's consider we have a topology. With that topology, my PC is connected with a switch, and I want that every day my switch will connect with the same LAN port which is connected with the same switch interface. So for that, what I can do is that I can bind my MAC address of my device to that particular interface of the switch, and I will configure switch port on that port security on that switch interface. So basically, what happens when someone else wants to connect his own device with that particular LAN port, so at that time, that switch will learn that it's a different MAC address which is not statically bind with me. So it will trigger the whenever switch will receive a request from a different MAC address, it will trigger the port security violation. And at that time, my switch port goes in the error disable state, and it will turn off the interface. If we have configured the aging time, then it will automatically come up. And if we are not configured with, if the switch is not configured with aging time, for that we have to manually shut down the port, and then we have again run a command to no shut command to turn up the switch port. So basically, this is the security measures we can do at our layer 2.
Okay, so if we talk about the violation modes in the port security, so what are the different violation modes?
So different violation modes is like restrict. We have sorry sir, I'm not that much clear about the states of violation modes.
Okay, so there are 3 different violation modes. Number 1, shutdown, which is the default. Then second one is restrict, and third one is protect. Okay. So both, like in the shutdown, what happens? The port goes to the error disable state, correct? In the restrict, the port does not go to the error disable state. And in the shutdown and restrict, what happens? Logs are generated. Okay. So the third mode, which is the protect mode. So in the protect mode, there are no logs generated. Is that clear? The port also does not go to the error disable state, and logs are also not generated. Okay. Now next question is, what is a firewall?
Firewall, sir, basically firewall is a security tool. We can say it's a cyber security tool which can sit in between our external and our internal network. And what it will do, it will analyze the traffic which is passing through the firewall, which is passing from internal to external. At that time, it will analyze the packet. It will take actions like deny. It will take actions like permit, or it will take actions like drop. So if there is a packet with a malicious file and that packet is not supposed to be go from the firewall, then at that time it will block the such type of traffic, and it will drop that packet also. So this is how our firewall sits in between our external network and our internal network, and will protect our network. It will do filtration for the traffic based on the rules.
Can you tell me about the generations of firewall?
So basically, yes, we have like we have next generation firewalls as well, and we have our basic firewalls as well. That is our ASA firewall. So what actually happens in those firewalls, and we have like some other for some other explanation, we can talk about stateless and stateful firewall as well. So basically, stateless and stateful firewall, what basically they did. So PIX firewall, we all are well aware about PIX firewall. That is a stateless firewall. What stateless firewall what it will do, it will analyze the packet, every packet as an individual packet, and it will take decision based on the source IP and destination IP, or the rules which are configured by the network admin. It will take decision based on those rules, and it will not maintain a state table also. So it will only inspect the packet, the individual packet. It will consider each packet as an individual packet. And in stateful firewall, it will maintain a state of connection, and it will analyze the behavior of the packet, and it will also maintain a state of the it will also maintain a track of that type of packet, so that it will, if it again receives the same packet with the same signature or with the same file, it will analyze the entire process, and then it will take actions. So basically, stateful firewalls, we have next generation firewalls as well. In our next generation firewalls, we have different features or blades, we can say. If we talk about checkpoint firewall, then we can say them as a blade, and that are anti-bot are IPS, IDS, and identity awareness, user awareness. So we can configure the rules based on not only on the source IP and on the destination IP, but on the identity and on the user. We can configure the rules, and this is how our next generations are different more than our basic firewalls.
When you talk about different generations of firewall, you can start by saying that, okay, first of all, we had packet filter firewalls, then we had stateful firewalls, application filtering firewalls, then we have next generation firewalls. Okay. All right. So next question is, let's say, what are the core differences between, stateful and stateless firewall?
So, sir, the core difference between the stateful and the stateless firewall is the same, which I right now told you, that in the stateless firewall analyze every packet as an individual packet. It will not maintain any state, or it will not maintain any connection table for that packet. If a request is going from our internal to our external, at that time it will take the decision based on the ACL, or we can say the rules which are defined by our network admin. And when the reply comes back, it will also take decision based on the rules. It will also inspect the reply as a different packet, not the same connection. But in a stateful firewall, it will basically maintain a state of the network, which is a state of the packet which is passing through the firewall. Whenever a packet is passing through the firewall from our internal network to external network, at that time my packet have to pass through my firewall. And at that time, when packet reaches to the firewall, it will maintain a it will maintain a connection table for that particular packet, and it will maintain a track for that packet. So if it receives the reply for that same the source IP and destination IP, it will take decision based on the connection table. It will see if there is any connection already generated in the connection table for this particular request or reply, and then it will take actions. So this is the core difference between our stateful and stateless firewalls.
What are the different types of rules?
So basically, sir, we have rules as like inbound rules, outbound rules we have, or explicit and implicit rules we have basically. So what explicit rules are the rules which are rules are the rules which are already there in the firewall. We can't change them and we can't modify them. But explicit rules are the rules which are configured by the user admin. In our explicit rules, we can configure rules like based on the source IP, based on the source port, based on the destination IP, based on the destination port, or else we can configure rules based on the user ID as well. We can create a user ID, or we can create a group of users, and we can configure rules based on that group of users. So that this is how we can create rules, different rules in our firewall. So basically, we have translation rules, we have access rules. So these are all the rules we have.
Okay. So in a LAN environment, how a switch is going to populate its CAM table?
So basically, sir, we have a switch. We have a switch. We have a firewall. We have a router. We have a switch. We have a What's up?
In a LAN environment, how a switch is going to populate or how a switch populates its CAM table.
So basically, sir, in the CAM table, switch will maintain the MAC addresses of the devices which it's learned. So basically, in the CAM table, how the switch is learning, how the switch is making or maintaining the CAM table is in the LAN interface is that whenever it receives a request from a PC, let's consider my PC is connected with the switch. At that time, my PC wants to communicate with a different. At that time, my PC wants to communicate with the different device which is already connected with the switch. So at that time, my PC will raise a request. In that request, there will be a source MAC address and there will be a destination MAC address. So when switch receives the request, it will check the source MAC address because switch will maintain its MAC address table based on the source MAC address, and it will learn the MAC address from the source MAC address, and it will maintain the connection table in the connection. It will maintain the MAC address table. In the MAC address table, it will bind my MAC address, my device MAC address with the interface from which it receives the request, and it will also mention the type, like dynamically it receives this MAC address or statically this MAC address is bind to the switch. So this is how switch will maintain its MAC address table.
Okay. Now, the next question is how STP is avoiding a loop.
So STP basically is the spanning tree protocol. What it did, basically the mechanism works in STP. They will choose a root bridge. Root bridge is the main point, or we can say main point for the entire network, which is connected with the particular, which is connected with the switch. So it will choose a root bridge, and based on the root bridge, it will choose the interface. It will choose the interfaces. So basically, we have four types of interfaces: a root interface, a root port, non-root port, designated port, and non-designated port. And this root bridge election happens with the help of BPDUs. That is our bridge protocol data unit. In the BPDUs, every switch will share its own information to the neighbor switch, and then the neighbor switch will share that information to the next neighbor switch. So on the basis of this BPDU, they will choose a root bridge, and based on the root bridge, they will block the redundant links. So the redundant links for the same destination they will block, and there will be only a one path for that destination, which is the closest path for the device. So this is how this happens, and the criteria for root bridge is first the lowest priority value, and if the priority value is a tie, then they will choose the lowest MAC address. So this is how STP works. They will choose a root bridge concept.
Okay. So you have worked with Cisco FTD or not?
Yeah, I have worked, sir.
So how Cisco FTD is different from Cisco ASA?
So basically, in Cisco ASA, we can't. We can only configure because Cisco ASA is not a next generation firewall, we can say, but Cisco FTD is the enhanced version of the Cisco ASA. In FTD will give us a GUI interface as well, and in FTD we can do filtration based on the application, based on the user ID, based on a group of users we can do. But in ASA, basically, what we can do is that we can only take decision based on the ports, or we can block some layer 7 application based on the ports. Like if we want to block HTTPS, then we can block the port number 443. But some applications are not directly using 443 port number. So at that time, all application layer protocols are not blocked for that particular one access list. We have to configure access list. So if we want to block layer 7 application in our ASA firewall, then we have to write a access list that is a who's task for the network admin. But in FTD, it's a completely next generation firewall, and in FTD, we can take decision, or the user admin can configure the rule based on the graphical user interface which is provided. And in that, it's very easy to configure the rules for the layer 7 applications as well. So in FTD, we can like basically we can say we can configure rules for application layer very easily. So and we have basically IPS IDS features also in our next generation firewall, so that we can also do.
Now explain the TCP header.
TCP header. So transmission control protocol, it's a layer 4 protocol. Basically, it's a layer 4 protocol, and transmission control protocol, it uses the protocol number as 6. So TCP header basically we have TCP header size of 20 bytes. But if we are using options and padding, then we can increase it up to 60 bytes. So the first thing we have in our TCP header is our source port and destination port. So source port is a 16-bit number, and destination port is again a 16-bit number. Then we have sequence number that is of 32 bits. After that we have acknowledgement number that is again of 32 bits. Then we have header length that is of 4 bytes. Then we have reserve bits that is of 6 bytes, and then we have TCP flags. Each flag is of 1 byte, and total we have 6 flags in our TCP header. So this is all of 6 bytes. This complete 6 flags are of 6 bytes. After this we have windowing. Windowing is again 16 bits, and after windowing we have checksum that is again of 16 bits, and after this checksum we have urgent pointer that is again of 16 bits. So this total is of 20 bytes, and after this at the end we have options and padding. Options and padding are of 40 bytes. If we are using these, then our TCP header size will increase from 20 bytes. If we are not using options and padding, then it will be the entire TCP header of 20 bytes.
So what are the differences between TCP and UDP?
So TCP is a reliable protocol because it uses the three-way handshake before establishing a connection to establish a connection with the destination device. But in UDP there is no concept of three-way handshake. In TCP, first what TCP will do, TCP will first the sender will send the synchronization packet to the receiver. That in that packet TCP will ask from the receiver that I want to establish a connection with you, and this is the port with which I want to establish a connection. Are you ready to establish a connection with this port? Then my receiver will acknowledgement back to my sender that okay, I'm this port is open, and we can establish a connection on this port, and it will also send a synchronization packet to the sender. Then sender will acknowledge the receiver's synchronization packet, and then they will establish a connection between the sender and the receiver. But in UDP, this is nothing. If a user wants to send a data to the receiver and they are using UDP protocol, so at that time they will not follow this three-way handshake. The user will directly send the data to the receiver, and there is no acknowledgement back for the data. Is that data properly reached to my destination or not? And in TCP, they are using acknowledgement and sequencing. Sequencing is basically when our user is sending a high amount of data, at that time number of segments are created, and to send the number of segments in a order, they will use a sequence number process. What basically sequence number is that on every segment they will add a sequence number like 1, 2, 3, so that my receiver will arrange all the segments in a order, so that it will receive the data exactly the data which is sent by the sender. But in TCP, there is no sequencing. If a user wants to send a data that is of high amount to the receiver, at that time there is no sequence number, and there is no data loss prevention also. In our TCP, we have data loss prevention also. Like we have selective acknowledgement option in our TCP. At that time, when a sender sending a huge number of segments to a receiver, and receiver receives 1, 2, and 3, but receiver don't receive the segment number 4, and it receives the fifth segment. So at that time, my receiver will acknowledgement back to the sender that I haven't received the segment number 4. So this is how the data loss prevention mechanism works in TCP. But in UDP, there is nothing like that. If a sender wants to send a data to the receiver will receive that much of data. But if data is not received by the receiver, it can't acknowledge back to the sender that I haven't received that much of data. So these are the core differences between the TCP and UDP. TCP, it's a reliable protocol because it uses a TCP three-way handshake process, but UDP doesn't do this. And TCP, it uses a protocol number 6, and UDP, it uses a protocol number 17. But both works on transport layer itself.
In between, you mixed a little bit for TCP and UDP, but rest of everything is good. Okay. Now, next question is, what is the difference between the push flag and urgent flag?
So basically, sir, push flag and urgent flag, these are the TCP flags. So basically, we have buffering concept in our TCP. So what happens with the push flag when a data comes, when a data with the push flag will do push the data, all the data which is already in the buffer memory, and it will push all the data which is already in the buffer memory, and it will transfer all the data to the application layer, and they will follow a sequence number as well. But what happens when a data comes with a urgent flag? So the data which comes with the urgent flag, it will not go to the buffer memory, and it will not push the data which is already in the buffer memory. It will directly processed, or we can say it is immediately processed to the application layer, and it will also break the sequence number. So the data with the urgent pointer is prioritized, and it will immediately forward it to our application layer. But the data with the push flag will first go to the buffer memory, and it will then push all the data which is already in the buffer memory, and then all the data is pushed to the application layer. So this is the main difference between urgent flag and push flag.
Okay, so what about urgent pointer?
So, sir, urgent pointer is only used when we have the urgent flag bit on. It is used to show which data is carrying the urgent flag bit on. When the urgent flag bit is off, then our urgent pointer is of no use.
Okay. Now explain the DNS process.
So, sir, basically DNS domain name system. So basically, it's a process whenever a device wants to connect with a web server. Let's consider I wants to connect with www.google.com, and I'm not aware about the IP address, public IP address of DNS, this www.google.com. At that time, what I will do when a user generates a HTTP request at the browser, at that time machines are not aware about the domain names. So if machine wants to communicate with that particular web server, at that time machine have to resolve the IP address for that web server. So for that, machine will hold the HTTPS request, and it will check the web cache and system cache first. Is there any pre IP which is already there in the buffer for this particular domain name or not? If the IP is there, it will take the IP from the buffer, and if the IP is not there, then it will proceed with the DNS request. So for the DNS request, first it will check the subnet mask of the DNS server. Is the DNS server in the same subnet in which my client PC is there? And if it's in a different network, then my client machine have to send the request via the default gateway. For that, if the DNS server is in a different subnet, and if the request is sent via the default gateway, it will hold the DNS request, and it will generate a ARP request for the default gateway. So when the default gateway receives the ARP request, it will reply back with its own MAC address to the client machine. Then client machine will use the default gateway MAC address in the DNS request, and it will forward the DNS request to my default gateway. When my default gateway receives the DNS request which is generated by my client machine, it will check the routing table. Is there any route for the destination IP address? If the route is there, it will forward the packet, but before that, it will also check the MAC address table. Is there any MAC address for that particular destination IP address? If the MAC address is there, it will use. If the MAC address is not there, it will hold the DNS request, and it will again generate the ARP request for the particular destination IP address. So now the ARP request which is generated by my default gateway reaches to my DNS server. My DNS server will reply back with its own MAC address to my default gateway, and my default gateway will use that MAC address in the DNS request, and it will forward the DNS request to my default. It will send the DNS request to my DNS server. Now at my DNS server, my DNS resolver will come, and it will take my request to the root server. So basically what root server will do, in our fully qualified domain name, we have a dot, hidden dot. After the domain name, we have a hidden dot. In our root server, that hidden dot is got resolved, and root server will see what is the top level domain name. In this request, we have www.google.com. So .com is our top level domain name. So my root server will give the information to my give the information about the TLD server, and my DNS resolver will take my request to the top level domain name. My top level domain name will resolve the .com, and it will see what is the particular domain name. It's a Google, so it will give the information about the authoritative name servers to the DNS resolver. And now my DNS resolver will take the request to the authoritative name server. Now the authoritative name server have the proper IP address for this particular domain name, and it will reply back with the IP address of this domain name to my default gateway. Now the default gateway will unicast this reply to my PC. This is how my PC receives the IP address for this domain name. Now my PC will generate a TCP three-way handshake with this destination IP address for a secure for a stable communication. After this TCP three-way handshake happens with the client machine and the web browser, then they will follow up with the SSL handshake because it's an HTTPS request. So for that, to secure our web application, they will follow up with the SSL handshake. After this SSL handshake, then my TCP request is got generated in our browser again. And then at application layer, my user will generate this request. After this request is got generated in the application layer, it will choose the protocol and it will choose the port number and it will forward it to the next layer. Now my request reaches to a presentation layer. At our presentation layer, my presentation layer will encode the request, it will encrypt the request and it will forward the request to the next layer. My session layer will establish a session with the help of RPC protocol, and it will, after establishing a connection for this particular request, it will forward the request to the next layer. So now my request reaches to my TCP. Now my request reaches to the transport layer. At our transport layer, as a part of an encapsulation, it will use a TCP header. In the TCP that is of 20 bytes, and now the request is known as a segment, and now the segment is now forwarded to the next layer, that is our network layer. At our network layer, as a part of encapsulation, it will encapsulate the request into a TCP header that is again of 20 bytes, and now the segment is known as a packet, and it will forward after this encapsulation, the request is forwarded to the next layer, that is our data link layer. So at our data link layer, it will encapsulate with the packet in the Ethernet header and in the FCS, that is again of 14 and 4 bytes. And after this, the packet known as frame, and this frame is then send it to the physical layer. And in our physical layer, that frame is our hexadecimal format data. It will convert it into bits, and then it will forward it to my and then it will send to my DNS server through the medium which is connected with. At our DNS server, the de-encapsulation happens at our application layer. It will convert the bits into the data and it will forward to the upper layer, that is our data link layer. As a part of de-encapsulation, it will remove the Ethernet header and it will remove the FCS, and it will forward the request to the next layer, next layer, that is our internet layer. Here, as a part of de-encapsulation, TCP header got removed and it will forward the request to the upper layer, that is our transport layer. At our transport layer, as a part of de-encapsulation, it will remove the TCP header and it will forward the request to the session layer. Session layer will maintain the session and it will forward the request to the presentation layer. Presentation layer again change the format of the data. It will it will again change the format of the data and it will forward the application to the it will forward the request to the application layer. So this is how my server receives the request which is generated with the client PC, and this all the process happens. This all the process happens with the DNS. So this is how the request is going from a client PC to a DNS server.
Okay. So can you tell me about some of the DNS records?
So sir, basically DNS records, we have AAA records, we have 4A records, we have MX records, we have SPF, we have DKIMI, and we have DMARC records. So in AAA records is the basically records for the IPv4 addresses, and in AAA records we have IPv6 addresses. In MX record is the text records we have basically, and in SPF is the sender policy framework which basically in SPF, which basically admin can define that which IP address can send the mail to that particular email domain name. So this SPF, DKMI, and DMARC are the DNS records which are used for mail exchange. DKMI stands for domain name key identification mail. So what it will do, it will generate a signature, or it will generate a digital signature for that particular email, and that signature is used to check the mail, is that mail correct which is sent by the sender, or it's manipulated in between. So these and this DMARC is the domain name which is used with SPF and DKMI. So these all are the DNS records.
There is no AAA. We have only A record which is pointing towards IPv4 address. Okay. It is only A record. And there is a pointer record which does the reverse thing. Okay. IP2 name resolution.
So for AAA records we have for IPv6.
4A record it is. Okay, so the next question I have for you is about the SSL handshake. Explain the full SSL handshake.
Okay, sir. So SSL handshake happens whenever we want to access a secure web server. So SSL is a secure socket layer. So basically, there are three main scenarios where SSL handshake happens. So this is the first scenario is when the server only have to authenticate. In that we have only 10 message exchanges. The second scenario when the client and the server both have to authenticate each other. In this we have total 13 message exchanges. And the last scenario which is used to resume a previously used session ID. In this we have 6 message exchanges. So I'm going to explain all the 13 message exchanges of SSL handshake. So the first message is the client hello. In the client hello, we have SSL and TLS version which is supported by the client machine. Then we have client session ID and client random number. After this, we have cipher shoots and we have extensions and compression method. Compression method is null, and in the client hello, the session ID possibilities are two. That the session ID can be null and it can be a number. If a number is there, then my server will understand that my client wants to resume a previously used session ID. And if the session ID is null in the client hello, so for that the server understand that the client wants to establish a new connection with the server. So after this, we have server hello. That is the second message. In the server hello, we have the same information, the SSL and TLS version, server random number, server session ID, cipher shoots, extensions, and compression method. After this, the server will exchange its own certificate. So the third message is the server exchange certificate. So server will generate a certificate and it will encrypt the certificate with the help of the private key, and it will share the certificate with the client. Fourth message is the server key exchange message. In this, server will exchange its own public key with the client. That is the corresponding public. This public key is the corresponding key of the private key, which is used to encrypt the certificate. So by using this public key, my client will decrypt the certificate and it will verify the certificate. The fifth message is server will ask the certificate from the client. So request a certificate from the client, and in the sixth message server will say server hello is done. The seventh message itself is the client certificate. Client will share its own certificate with the server. It will encrypt the certificate with the public key which is shared by the server, and it will share the certificate with the server. Now server will use the private key to decrypt this certificate and it will check the certificate. In the meanwhile, client will also verify the certificate which is issued by the server. It will check the certificate authority, is that trusted. It will check the expiry date of the server. Then client will generate a pre-master secret key with the help of server random number and server session ID and client random number and client session ID. And it will share the pre-master key. It will encrypt the pre-master key with the server public key, and it will share the pre-secret master key with the server. Now server will decrypt it with the help of private key, and then they both will generate by using this pre-secret master key. Then they both will generate a secret master key, and this secret master key is used for the encryption and decryption of the actual data which is passing in the request and the response. And then after this pre-master key and pre-master key and secret master key, then my client will change the cipher shoots and it will send the 11th message, that is finished from client side. In the 12th message, server will change the cipher shoots, and in the 13th message, server will send the finish message to the client. So this is all the process happens in the SSL handshake.
Okay. So the next question is about the IPsec. Explain IPsec.
So IPsec, it's an Internet Protocol Security. It's not a single protocol. IPsec, it's a suite of protocol. So basically, we have three main protocols under IPsec. IPsec, the one is ISACAM, ESP, and AH. ISACAM stands for Internet Security Key Association Protocol, and in ISACAM we have basically two versions, IKEv1 and IKEv2. ESP stands for Encapsulation Security Payload. It uses a protocol number 50, and it's a and it supports both hashing and encryption. But protocol, it uses protocol number 51. AH stands for authentication header, and it only supports hashing only. It will not support authentication. So basically, AH is used in our monitoring and testing purpose, but ESP used in the entire physical network. So the main protocol which is used in ESP, that is for the actual data. So basically, so now ISACAM. So ISACAM, we have basically two versions, IKV1 and IKV2. In IKV1 we have two phases. Phase 1, that name is ISACAM, and phase 2, that name is IPsec. So under ISACAM phase 1 we have basically two modes, main mode and aggressive mode. And in phase 2, that's name is IPsec, we have only a single mode, that is our quick mode. And in our IKV2 we have basically two phases. Phase 1, that name is ISACAM IKSA init, and phase 2 name is IKOth. There is no mode concept in our IKV2. So in our IKV1 phase 1, that is our ISACAM, we have main mode. In this main mode we have 6 message exchanges, and in our aggressive mode we have 3 message exchanges. And the secure combination which is used is the main mode plus quick mode. Total 9 message exchanges are there. So in IPsec main mode we have the first message, that is from the client side to the receiver. In this is the proposal message to the receiver. In this we have basically security parameter index, security association payload, and we have vendor ID payload. In a vendor ID payload we have basically a hash value that supports the NetT. Is that device supports the NetT condition or not? In our security association payload, basically we have, under the security association payload we have proposal payload. Under the proposal payload we have transform payload, and under the transform payload we have Haggle process. In the Haggle process, H stands for hashing, A stands for authentication, D stands for Diffie-Hellman group, S stands for lifetime, E stands for encryption. This is the proposal sent by the client, and this is all the information which is shared by the client in the first message to the server. Now server have to accept this proposal, and it will reply back with its own information. The same information is sent in the second message. The same information, the vendor ID payload, security association payload, and SPI shared from the server to the client. In the third, or the peer to the different peer. In the third message itself, we have nonce value payload, we have Diffie-Hellman key exchange payload, and we have NetD payload. In the Diffie-Hellman key exchange payload, they will exchange their public keys. They both will generate a pair of key, and they will share their own public key with the peer. They will not share the private key they will keep with themselves, and the public key they will share that with the peer in the Diffie-Hellman key exchange payload. The next payload, that is our NetD payload. In the NetD payload they will generate a hash value based on the source IP and the destination IP, source port and the destination port, and then they will, with the help of this NetD payload, they are trying to discover is there any is there any translating device in between both the sites or not. And in the nonce payload there will be a numerical value used for replay protection. So this all information in our third message. The fourth message is the reply message for this particular third message. The same information is there, the nonce payload is there, Diffie-Hellman key exchange payload is there, and the NetD payload is there. In the fifth message itself, they will share a authentication and a identity payload that is encrypted, because the Diffie-Hellman keys are already shared in the third and fourth message. So in our main mode, fifth message, identity and authentication payloads are shared in an encrypted format, and the site 1 will share the identity and authentication payload with the site 2, and in the sixth message site 2 will authenticate itself, and it will share its own authentication and identity payload. So basically the main difference we have with our aggressive and main mode is that only in our aggressive mode our identities and authentication happens in a clear text, but in our main mode it happens with a cipher text, because the keys are already generated or already shared. So in our aggressive mode basically we have 3 messages. So in this, the first message itself will carry all the information which are shared on the first six messages in main mode. So in our aggressive mode, first message itself, we have everything like we have security association payload, we have security parameter index, we have netd payload, vendor id payload, Diffie-Hellman key exchange payload, authentication and identity payload, nonce value payload, netd payload. Everything we have in our first message itself. In the second message, the second message is the reply message, and in the third message itself, they will do a authentication that this both the sides are okay with each other. So these all the three messages that is of aggressive mode. Then we have come to our IPsec. In IPsec, we have basically three messages. This is the phase 2. So all all the messages of IPsec, main IP, all the three messages of quick mode, all the six messages of main mode, and all the three messages of aggressive mode carried under the protocol ISA-CAM. If there is no net T device in between, ISA-CAM will use UDP port number 500 for both source and destination. And if a netd payload is there, then the port number is changed to UDP port number 4500 for both source and destination. So this is all about the IPsec.
Okay, so the next question is, what are the different types of VPN?
So sir, different types of VPN we have site to site VPN, routed VPN, and policy based VPN. So in policy based VPN, policy will take decision for which traffic will go through the tunnel. But in routing based VPN, the routing table will take decision which traffic have to pass through the VPN. So basically, we have two types of VPN: policy based VPN and routing based VPN. And under these, we have more types of VPN like DMVPN. We have point to point VPN. We have site to site VPN. We have multi point VPN. We have.
So next question is, what is the difference between MGRE and DMVPN?
MGRE
and DMVPN.
So sir, basically in DMVPN, we have a let's consider we have multiple sites, and we want that all the multiple sites can communicate with each other. So at that time we can go through the dynamic multi-point VPN, that is our DMVPN. In this, what actually happens is that every site is not initially aware about all the sites. We have basically our headquarter. That headquarter have all the routes to all the sites, but all the branch sites have the route to the headquarter only. In this, what basically all the branch, if the branch wants to communicate with a different branch, at that time first that branch have to send the request to the branch have to send the request to the headquarter. From the headquarter, they will download the route for the different branch, and then they will communicate with the different branch. So this is the process happens in the DMVPN. And about MGRE, I'm not sure about MGRE, so I can't give false information. So about MGRE, I'm not that much aware about, and DMVPN, I'm aware about this much I know about DMVPN.
So explain the concept of private VLAN.
So private VLAN. So basically, sorry sir, I'm not aware about it.
Okay. Explain VLAN.
So VLANs are basically it's a layer 2 technology. What VLAN stands for virtual local area network. So basically, VLAN works on our switches, and by default, our switches have a single broadcast domain. To break down that single broadcast domain into multiple broadcast domain, we use VLANs. So basically, what VLAN will do, VLAN will convert VLAN will break down the single broadcast domain into multiples. Each VLAN can communicate with the same VLANs by default. So if two VLANs wants to communicate with each other, then we have to go through the inter-VLAN routing process. In that, we have to make our interface as a trunk. So this is the process of the VLAN.
Okay. What is the difference between forward proxy and reverse proxy?
So, sir, forward proxy. So basically, for what forward proxy will do. So forward proxy, let's consider we have a web security appliance, that is our WSA, and we have to configure that WSA in our local area network so that we can monitor, or we can filter out our web traffic with the help of our WSA. WSA is our forward proxy. It sits between the client and the web browser. It sits between the client and the external internet, and it will hide the main IP of the client, and it will translate the client IP to itself, and then it will forward the request to the web server. So it sits between the client and the internet, and it will forward the request which is generated by the client to the web server. And what reverse proxy will do, in reverse proxy, we have basically web application firewalls. We have these web application firewalls are known as reverse proxy, that sits inside the internet itself. When let's consider we have a web application server. In that web application server, we want to give a security for that web application server. So for that we have to deploy a web application firewall, that is nothing our reverse proxy. So what this reverse proxy will do, it will analyze the request which is coming for the web server, and it will analyze also the reply which is going from the web server. So this is the main difference.
Okay, and what is the difference between transparent and explicit proxy?
Yeah, transparent and explicit. So this is the implementation method, sir. Transparent redirection is only happens when we have a Cisco device as a default gateway. So when we have transparent redirection, what basically happens is that there is a protocol known as WCCP protocol, Web Communication Cache Protocol, which is used for redirection, and we have to configure this protocol on both our WSA device and on our default gateway device. So whenever the client, let's consider WSA deployment happen with a transparent redirection. So then what will be the data flow? So when the client generates a HTTPS request, first that request go to the default gateway. On our default gateway, it will see, okay, it's a web request. So for that, there will be a ACL which will block this request, and there will be a WCCP protocol which will redirect this request to my WSA. So this WCCP protocol will redirect the request from default gateway to WSA. Now WSA will analyze the request. If the request is triggering any security policy, it will drop the request, and it will reply back to the user that you can't access this website. This website is blocked by the admin. And if the request is okay to forward, then it will do the translation. It will change the IP of the user, and it will make a source IP as its own IP, and then it will forward the request via the default gateway. But in explicit forwarding, what actually happens is that my default gateway is not aware about the WSA deployment. In explicit forwarding, we can configure the proxy settings in our client PC itself. We will tell the client to use this proxy to send the web requests throughout the network. So in this, what the data flow is that when the client starts a request, at that time the request reaches to my WSA directly. It will not go to the default gateway. Then from WSA it will take decisions, and then it will forward it to the internet. So this is the main difference. In explicit forwarding, my client is aware about the WSA deployment. It will directly forward the request to the proxy device. But in transparent redirection, my client is not aware about the WSA deployment in the network. First, it will send the request to the default gateway, then default gateway will redirect the request to the WSA.
Okay, now can you explain the email exchange flow?
Yes, sir. So basically, email exchange flow. Whenever a PC wants to send an email, at that time what actually happens? We have basically SMTP protocol, that is simple mail transfer protocol, which is used to send the mail from the client PC to the from the sender's PC to the sender's mail server. When the senders want to send a mail, at that time SMTP protocol is used, and it will use a by default encryption port number, that is 587, That is the by default mail submission port number, and it's an encrypted port number. It will use SMTP 587 port number to send the mail to the sender's mail server. At the sender's mail server, when the sender's mail server receive the mail, it will check the destination domain name, and throughout the SPF and throughout the DKMI and MX record, it will see if this particular IP is able to send the mail to the if this particular source IP is able to send mail to this particular email domain name. If everything is okay, then with the help of MX record, it will find out the IP for this mail, and then the sender's mail server send the mail to the receiver's mail server with the help of SMTP protocol. Here also SMTP protocol is used. But when the email received at the receiver's mail server, to retrieve that mail, receiver's device will send a request with the IMAP or a POP3 protocol. So POP3 stands for Post Office Protocol version 3, and IMAP stands for Internet. IMAP. So basically, IMAP will use port number 993, that is the encrypted port number, and POP3 will use port number 995. Port number 995, that is also an encrypted port number. So these are the two protocols which are used from the receiver PC for retrieve the mail from the receiver's mail server. So this is how the mail sends from our senders to our receiver.
Okay. Now, the next question, what is the difference between MTU and MSS?
So basically, MTU and MSS. MTU is a maximum transmission unit. These are the two options of TCP, and MSS is the maximum segment size. So MTU, what is MTU? So MTU is the MTU we can consider it's a 15 MTU is a 15 bytes of segment. In that we have 20 bytes of TCP header, 20 bytes of IP header, and then 1460 bytes of data. And that 1460 bytes of data is nothing are MSS only. So MSS is the maximum segment size, is the actual size of the data which we have in our segment. If we have IPv4, then the MSS size is 1460 bytes. If we have IPv6, then the MSS size is of 1440 bytes. And sometimes we can see that our MTU size is 1518 bytes also, and that will be considered as a jumbo frame also. So at that time, what actually happens is that 14 bytes of Ethernet header and 4 bytes of FCS is also considered in our IP MTU. So this is the difference. This is the MTU and MSS.
Okay. So please explain about DHCP and the messages.
Okay, so DHCP uses two different port numbers. It's a dynamic host configuration protocol. It is used to configure automatically IP address to the client machine. It uses 67 and 68 port numbers, 67 for server and 68 for client. So in DHCP, it will basically follow a DORA process. In DORA process, we have basically 4 messages. That first message of DORA process is a discover message. Second message is a offer message. First message is a request message, and third message is a request message. Fourth message is a acknowledgement message. So what basically the client will send a discover message to the DHCP server. In the discover message, it will send in the discover message, source IP and destination IP is 000 only. Destination MAC address is a broadcast, and source MAC address is the PC's MAC address. When this request reaches to my DHCP server, it will see the DHCP pool. If the DHCP pool have the IP, then it will offer a IP to the client machine with the help of offer message. In the offer message, the source IP is of DHCP. Source IP is of DHCP server IP. Destination IP is again broadcast, because still our client don't have the IP, and the source port is our source MAC address is of server's MAC address, and destination MAC address is of client MAC address, and then it will forward the message to the client. In this offer message, the IP is there. So when the client receives this offer message, it will generate a GR process. That is, a GRP is used to find out the duplicacy of the IP. So which IP is offered by the server to the client. To check the duplicacy of that IP, it will generate a GR process, and it will, in the GR, destination MAC address is the FFF, and source IP and destination IP is same. So if it receives a reply back for that GR request, So if it receives the reply, it will find that there is another device which is using the same IP, and it will drop the IP here itself. And if it not receive the IP, then it will find out that this IP is a unique IP, no other device is using the IP. Then it will send a request message to the DHCP server. In that request message, it will use the DHCP options. That options will carry the IP which is offered, and then it will request this IP to the server that okay, this IP is fine for me, and assign this IP to my PC. And then for this request message, DHCP server will send an acknowledgement back to the client PC. In the acknowledgement also, the source IP is of DHCP server, and destination IP is again broadcast, because still our PC don't have that IP. After this acknowledgement, only PC will configure this IP on the interface. So in the acknowledgement, that is the last message of the DHCP process, DHCP DORA process, and in the acknowledgement, it will the server will acknowledge the requested IP from the client side. So this whole process happens in the DHCP.
Okay.
And basically, we have 4 more messages of DHCP. That is our DHCP info message, DHCP decline message. So the more 2 messages I am not aware about, but these 2 messages I am aware about. So when
you have DHCP decline is there, DHCP negative acknowledgement, release, and inform.
Yeah, release and inform, right? So.
Okay. Okay. So explain about DHCP snooping and dynamic ARP inspection.
So basically, DHCP snooping happens when we have 2 or more DHCP servers in our network. So what is DHCP snooping? Whenever a PC sends a request, discover message to the network, and some guys with the bad intention, or we can say some hackers, are there inside the internet when the DHCP server is in a different network. At that time, they will send a reply back to the client instead of that particular instead of the main DHCP server. Some fake DHCP server will reply back to the client. So this is the DHCP snooping process. And dynamic ARP, I'm not aware about, sir.
My last question to you: what is the difference between IDS and IPS?
So, sir, basically, IDS stands for Intrusion Detection System, and IPS stands for Intrusion Prevention System. So, basically, what IDS is the previous version of IPS. So, IDS will basically what IDS will do. IDS will detect the file, and it will generate an alert to the user that this is a malicious file. It will. So, basically, this is a malicious file. The signature of this file is not match with the signature database, and it will generate an alert, but it will pass the file. It don't have that authority to drop the file, but IPS have that authority to drop the file. Because what basically IPS will do, it will analyze the file. If the file is not matched with the signature database, if the file signature is not matched with the IPS signature database, it will generate an alert and it will generate the file. So this is the main difference. IDS will not drop the file, it will only generate an alert to the system admin, but IPS will also generate an alert and it will also drop the file.
Okay. So those were all the questions, and you are quite well prepared.
Thank you, sir.
Okay. So to the people watching, these were all the questions. I hope these questions helped you in your preparation also. And Praveen, I wish you all the best for your future endeavors.
Thank you, sir.
To the people watching, if you like this video, if you find this helpful, do like the video and subscribe to the channel. We'll see you guys in the next video. Bye-bye.